Let's do another example using the method of initial rates to find the rate law. And don't use this as the first one to watch because I'm going to go a little faster through this than I did the first example. So this is a bromination example. We're adding bromine to acetone. C3H6O is acetone. The problem says determine the rate law and the rate constant. And temperature, we don't need the temperature. This is being done at room temperature, and since that's not changing, the rate constant is not expected to change, which means we don't need that information. So let's write out the general form of the rate law. Rate equals the rate constant. Then we pull the reactants down. That's the concentration of acetone raised to the x power, and the concentration of bromine raised to the y power. Now at this time we have one equation and three unknowns. We don't know k, x, and y. So we need to find a way to manipulate this information to turn it into one equation, one unknown. And we do that by picking two sets of data to compare to each other. And I'm going to choose trials 1 and 2. Since the concentration of acetone is changing and bromine is not, that means we're going to be looking for X first. Just shift things up to make some room. Okay, so we take the rate law from one of them and divide it by the rate law for the other one. So we start off with the left side of the equation. And I'm doing trial 1 over trial 2. And a reminder on units. I choose not to show the units when determining the rate law with this method just because it gets kind of busy. If you want to show the units, you can. Now for the right side of the equation, since we're doing trial 1 over trial 2, I have to put in the information for trial 1 in the numerator and trial 2 in the denominator. Now the reason why we're doing this, we can get rid of some things. Whatever k is, it cancels out. Whatever y is, it cancels out. So I just removed two of the three variables. Just shifted some things around to make room. So let's reduce this down. The left side is 2.60. I remove some information from the right side. So we have the numerator and denominator each raised to the same power, so I can consolidate under the parentheses, and so that whole thing is raised to the x. That lets me do the division in the parentheses. So 2.6 raised to what power is 2.6? You see, it's not an integer, the 2.60, but you can do this. That's 1. So now we have the order with respect to acetone. All right, so let's look at our rate law. We start with this. We know that x is 1. You don't have to actually write the 1 down. Now we need to find y. So I'm going to choose to compare trials 1 and 3 to each other because the concentration of bromine is changing while the concentration of acetone is not changing. Now notice that the initial rates are not changing. I wonder what that means. Let's carry on. Just making some room. Divide the rate for trial 1 by trial 3. That's the left side of the equation. And now we have to do the right side of the equation. So that's for trial 1. That's for trial 3. We'll eliminate k. And it's 0.13 over itself, so that goes away. So just like before, make some room. So let's do the left side. Well, you know that. That's just 1. Clear up the right side a little bit. Numerator and denominator both raised to the same power, so we'll consolidate the information. And we'll take care of what's in the parentheses. Oh my gosh, how to do that? I mean, that's terrible. 0.409 raised to some power is 1? Oh my gosh, what the heck is that? Any number raised to this value is 1. It doesn't matter what the number is. So what's y? Y is 0. Anything to the 0 power is 1. Alright, so let's write out the rate law. This is where we were. Now we just figured out y. But again, anything to the 0 power is what? It's 1. So let's remove that. We don't even need it. So there's our rate law. Be careful on your interpretation of this. This appears to say that you don't need bromine. That's not what it says at all. What it really means is there's a minimum value needed for the concentration of bromine. Once you meet that threshold value, if you have a higher concentration of bromine, it doesn't affect the rate. See, if you look at this and go, oh, I don't need bromine, well, but look at the chemical equation. It's got bromine in it. So this is what happens when you have one of the reactants is 0 order. You change the concentration of that reactant and you do not expect it to have an effect on the rate. And if you compare the rates for trial 1 and trial 3 in that table, that's what you see. You change the concentration of bromine and the rate doesn't change. Now there's the rate law, but we want the rate constant also. So we'll rearrange and solve for K. That's rate divided by acetone concentration. And like I explained before, it doesn't matter which trial you pick to do the rate constant unless you're specifically told to use all the trials. Since you're not, you can use any of them. So let's look at the value as determined from trial 1. So there's our mathematically manipulated rate law down below. So we pull the rate out. I have my units now. You have to put your units in when you determine the rate constant. The rate constant has units in it. And then divide it by the concentration of acetone. And you get this value numerically, and there are your units, 1 over seconds. Now you could do the same thing for trials 2 and 3. I won't actually go through that this time, but here's a table that shows the values from all 3 trials, and they do happen to come out the same, at least to three significant figures.